All right. Good evening, everybody. It's kind of tough to come in because we had no undergraduate class today, so felt like a day off. And then I kid you not, I remembered at lunch we had class tonight. So it's this close to me not being here and you being here and be very angry at me. So I did remember though, so it's a good thing. We are, I think we are at week 9 of the class, so this is the 18th. We talked last week about, I heard some of you guys talking before class about your group projects. So today's material is chapter 6, which is decision analysis, which is probably, of all the things that we cover in this class from chapter 1 to 8, I think it's the easiest chapter. So we'll have some time left at the end of this class is what I'm projecting anyways. So hopefully you can maybe try to partner up and try to think about some topics at that point. But what we're talking about last class was we talked about project scheduling techniques. So, I told you the field of project management is pretty vast. There's all kinds of things associated with project management, risk assessment, quality, procurement, all those good things. But one of those things that we talk about as part of project management is scheduling tasks and deciding what is the critical path and what tasks and activities have slack and what's the early start to early finish, late start, late finish. And then going from that to putting some variability on each of the tasks so that we can put variability associated with all the projects. So I think I assigned you 4, but I think the best one that I'd like to do that I think kind of dealt with some of the attributes that we can discuss is number 7. This is on page 313. So it says George Washington High School is planning a reunion for the graduating class of 1975. The D'Onofrio twins, who were in charge of planning the entire event, have determined the following tasks. So looks like we have 9 tasks here, maybe. Yeah, 9 tasks. They have put them together with some predecessors. And they're also saying that we don't know these tasks with certainty, so they're using the 3-time estimate approach, which is also used sometimes for cost estimation as well. And in that approach, we use 3 times or 3 costs. We use a best case scenario, a worst case scenario, and a most likely case scenario. Each of those things, we get 1/6 of the weight goes to best case, 1/6 to worst, and 2/3 or 4/6 to probable. So it's kind of a weighted method. And then the standard deviation assigned is worst case minus best case divided by 6. So we don't have to worry about that so much because we have in chapter 5, we go to material by chapter, chapter 5, we understand that we have a template that will take care of that for us. And this template is using, behind the scenes, it is using constrained optimization model. So if we go to chapter 5, we go to Blackboard, it says PERT CPM template, and we give it a few things. So just going to come over here, and basically at this point, we're just kind of copying the information where it needs to go. Now, this is on page 313. So activity A is determined. I'm not going to type all this out because you're not going to want to watch me do that. But I'm going to, whoops. I'll just use B, C, D, E, F, G, H, and I. Okay, so we have the activities, and we'll change that to A, and we'll change that to B. Okay, so we have the activities. We can write in the names, then it auto assigns a letter to that activity, a node name, A, B, C through I. So for each of these, the 3-time estimate approach is A, M, B. So the first one is 20, 25, and 50. That's activity A. B is 3, 5, and 12. Activity C is 10, 14, and 21. Activity D is 5, 14, and 18. Activity E is 10, 10 and 14. Activity F is 8, 14, and 25. G is 3, 4, and 7. H looks like it's 32, 40, and 50. And finally, I is 2, 5, and 8. Okay, so we have the activities. We have an estimated duration for each of those activities. To do per CPM, we also need to know the dependencies. And that's what the chart gives us when it says immediate predecessor. So it doesn't look like A and B wait on anything, but it says that C waits on B, and D also waits on B. So that's how we read that chart. It doesn't look like E waits on anything either. F waits on A and C, so I have to enter that twice. F waits on A, F waits on C, G waits on B, and H waits on D, H waits on F, and H waits on G. I waits on E, and I waits on H. Okay, so the moment of truth, I think we have all the information in. We're going to go to data, solver, solve, finds a solution, but nothing changes because remember, there's some hidden fields here, some hidden columns. It's just priming those. I go to the per output tab. We also see that solver is already initialized for me here. I click OK, keep solver solution. And I get an answer. So it tells me the average. Did you guys get that? Is this in right?
The last one, we typed in E, waits on H instead of I.
Which one? So
The very last one.
E waits on.
I waits on H.
This one.
The very last one.
This. All right. So we're going to have to. Oops, that's going to be. Let's solve it again. All right, I solve on the input tab. Hopefully it'll work this time. I'm going to solve it on the output tab. And I get 88.5. Is that what you guys got? Okay, so these are a little bit cumbersome, right? The little kind of clues you make one little mistake and it throws off my answer. But we have some information now that we can analyze with this project. For example, we expect the project to be done in 88.5 days. And we also know the critical path activities, which is what? What are the critical path activities? Very good. A, F, H, and I. Those are the activities defined that have no slack. It's the longest path through the network. Any delay to those activities will delay the overall project. We also know that we have, looks like 5 activities that do have slack with, this is what F has, E maybe? So E has the most slack of 72 days. So it can absorb it. Now, all this variability kind of adds into the variability of the overall project. And it's telling me the project has a mean duration of 88.5 days. So if my boss asks me, she says, what percentage of the time, what's the probability you'll be done in 88.5 days? I can tell her what? What's the probability you'll be done in 88.5 days or before? 50%, because it's right in the middle. 50% of the time I'll be done longer than that. I think what we're looking for right here is have to commit, what's the probability that they will have to commit more than 90 days? So we're looking for 90 days or more. Okay? If I put in 90 in the probability complete before, it gives me 59%. Let's just call it, well, we'll call it 59%. That's 90 days or before. So what's the odds that we're going to spend more than 90 days? It would be 1 minus that, 1 minus 59%, and that gives me 41%. Okay? So that can be very useful to me. If my boss told me, I'd love you to get this project done in under 60 days, I could say, well, hey, I don't think that is possible. According to this, the odds of that occurring is very, very, very low, unless we do something different, like we crash the project, we add some resources to it. At this point, it's not very, very likely. Okay. So that's how we would use this in a business environment. Any questions about that? You guys able to do the homework okay? Anyone use a Mac have issues with this? I know one student has. Anyone else able to do it with a Mac? It works on your Mac? Okay. Do you know what Excel version you're running, Tiffany? Okay. So it's a pretty recent one? 2016 maybe? No? Okay. All right. So any questions on project management? All right. Well, as I said, we do offer, I think it's going to be offered in the spring. I think Mr. Tonkin is teaching a online section of project management. It's called IT project management, but it doesn't really assume that you need to know a lot about information technology. It's just, information technology is a field of change, so project management goes closely along with that. But project management is a general skill. If you're building roads, you need project management. If you're planning a wedding, you need project management. So it'd be a good class for many of you to take. I think it's an elective class. All right, so let's move forward, and we're going to move to chapter 6. So we're going to move into chapter 6, and I think I told you chapter 6, I think may be the most straightforward of all the chapters we cover. It's useful, but it's probably something you encountered as well in your undergraduate studies. Usually in maybe a production operations management class, you may have encountered decision models. And so we've been talking about making decisions. Business is about Management is about making decisions and using finite resources the best possible way. So we're going to try to put decisions in a framework. So a lot of times we make a decision by gut feel, or we have some information, but we're going to try to put together a framework that allows me to apply basically a little algorithm to pick from a bunch of decisions that I can make. Obviously, like we've been doing all along, our goal is to optimize a resulting payoff in terms of some decision criteria. Things we typically optimize, maybe expected payoff. Okay, expected profit is something that we want to maximize. We can also talk about maximizing utility. Utility is different. Utility has to do with happiness, right? The happiness that I get from $100 may be different than the happiness you get from $100. So we'll talk about expected value. We'll also talk about expected utility. So to start, we have to kind of define a tool that we're going to use. And that tool we're going to use is something called a payoff table. And I'll kind of draw it up here so the screen can capture it. A payoff table looks like this. And it depends what text you're using, but we're going to put the decisions on the rows. So in this case, I can make one of three decisions. We'll call it decision 1, decision 2, and decision 3. And these decisions are affected by something. Okay, so these are we call these decision alternatives. And they're affected by some unknown event. And we're going to call that a future state of nature. Because it's something we do not know. We'll say state of nature 1, state of nature 2, state of nature 3. And the way we read this is we're at time current, and if we make decision 1 and this happens, whatever this is happens, we get this payoff. So if we make decision 1 and this occurs, we get $100. If we make decision 1, and I'm just putting arbitrary values in here, and this occurs, we're making decision 2. I'm sorry, we're getting $50. If we make decision 1 and this occurs, I don't know, maybe we make $200. If we make decision 2 and this occurs, hey, maybe that's a $500 profit. If we make decision 2 and this occurs, maybe we lose $500. And if we make decision 2 and this occurs, maybe that's another $200. If we make decision 3 and this occurs, let's say that's $250. Let's say that is negative $200, and let's say this is $100. Okay? So this is how we read it. These are the decisions we can have. And these decisions are finite and mutually exclusive, meaning we list all the possible decisions and there's no overlap between them. We either make decision 1 or decision 2. The same thing for the states of nature. They are finite, we can list them all, they're not infinite, and there's no overlap. Either this happens or this happens. We can't have a little bit of both. Either we fall into this or we fall into that. Now sometimes there are 2 events that occur up here. Maybe what happens in the stock market and what happens to the price of gold. Well, we have to look at combinations of those things to define uniquely the future states of nature. So if we looked at this situation, this is a payoff table. And sometimes, oftentimes, this is the hardest thing to construct, because if we're here, we make this decision, these are projections. We project if we make decision 1 and this occurs, hey, we make $50. If we make decision 2 and this occurs, I'm projecting we lose $500. Okay, and this could be thousands, this could be hundreds of thousands, this could be millions, but these are projections typically. Projections. Usually we'll use forecasting to kind of come up with those, which we'll talk about in chapter 7. Okay? So if this was presented to you, what decision would you make? If this table was presented to you, I'll pick on someone randomly, what decision would you make? Okay, so Lori says decision 2. And why Lori? You can't be wrong. Why do you say decision 2?
I just see 500, the biggest number.
All right, so you are maybe an aggressive decision maker. I don't know, Lori, but I'm based on this little exercise, I'm making that assumption because you see a big number like 500, but you also see a big negative 500, but you say, the hell with that. I'm going big or going home, right, Lori?
Pretty much.
Okay. So that's your decision. Anyone else? Damon?
1.
Okay, why 1?
Because you never go broke making a profit.
Okay, so $150, $200, you're saying there's nothing there that scares you, right? There's no negatives. You're saying, I'll take those small returns, but okay, that's fine. That's your so maybe you are a little bit risk averse. I don't know, are you? No, okay. In this exercise, you are?
Exercise, yeah.
All right. Anyone else? Would anyone choose decision 3 at all? No? Okay. Maybe someone would. Maybe they're moderate, says, I can sustain a negative $200 loss, and I like that 250 there and 100, so maybe I could sustain that. So what we're going to learn in this class is once we're able to take a decision and put it in a payoff table of states of nature, we will learn criteria we can apply to that. Decision criteria that we can utilize, that we can apply to that. So this slide kind of does what I showed you. It says a payoff table can be applied when there's a finite set of decision alternatives, and we saw that in my table there was only 3. The outcome of a decision is a function of a single future event. And I said single future event, but it could be a combination. Like event A means B and C occur, and event X means B and C didn't occur, right? So we can combine things to come up with a single event. The rows correspond to the possible decisions. The columns correspond to the future events, future states of nature. They are mutually exclusive and collectively exhaustive. Mutually exclusive means no overlap. Exhaustive means, we're covering everything. There's everything that could happen is involved there. The table entries are the payoffs. So that's what we saw. So a couple other things before we go into the Tom Brown case. There are different states, and I don't know why the slides don't have this, but there are 3 different states we make decisions under. The first one is certainty. And certainty is, we know what's going to happen, right? I know what's going to happen, the states of nature. So if I told you, in this case, state of nature 1 is going to happen, well, hell, that's an easy decision. I'm going to pick decision 2, right? If I told you I know state of nature 2 is going to happen, you're like, oh, that's an easy decision. I'm going to go with decision 1. But there are situations where we have certainty when we make decisions. We know what's going to happen. It still might be a difficult decision. We know if we do A, B will occur, but we're not sure we want B to occur. Okay, so we're not really going to talk about certainty, okay, in this class. We're not really going to apply any models to certainty because it's more it's more preference than anything else. But the two areas we make decisions we're going to talk about in this class is uncertainty. I don't know if I spelled that right, but uncertainty means we have no clue what's going to happen. We don't have an inkling. We can't predict it. We don't have any inkling about what is going to occur in this future state of nature. We say, we have no clue what the likelihood of this is going to occur, or this is going to occur, or this is going to occur. We don't know if this is 10% or 99%. We don't know if this is 30% or 85%. That's uncertainty. The third one is when we do have some likelihood, some knowledge, we can put a probability on those states of nature. What do we call that? What do we call that? We call that decisions under risk. Okay? Decision making under risk. If we can put a probability to it, 10%, 50%, 90%, that's no longer uncertainty. We say there's a 90% chance that we call that decision making under risk, and we're going to use that probability along with our decision. By the way, this is next week, so maybe we should talk about it then. Who's going to win the presidential election? Talk about forecasting and who's going to win. And I'm not telling you who I'm voting for because teachers shouldn't do that, professors shouldn't do that, but who's going to win? Damon, who's going to win?
Gary Johnson.
Okay. I think it's less than 0.1% that Gary Johnson wins. Factual. Who's going to win? Okay. What would you assign a probability to that, Eric?
Off the top of my head.
Yeah, go ahead.
60.
Anyone else? Anyone lower? No. Guys aren't going to play. Anyone higher? Just all go over there, 60%. If you go to, this is a site I really enjoy. If you go to you guys use 538 at all? Is it here? Yeah, it's probably at 87%, right? Yeah, at 87.6% right now. So This is Nate Silver, is a statistician, economist. Oh, you guys can't see this. He's a statistician, economist. And last year, the last 4 years ago, in the 2012 election, he accurately predicted every single state. So he predicted the election correctly. I think with like a month ago, he had every single state correct. So how does he do this? How does he do this? So he's saying right now, there's an 87.6% chance that Hillary wins the election. So how does he do that? What information does he have to do that? Okay, very good. So that's a method called inferential statistics. We can't ask everyone, we don't know what everyone's going to vote for, but we take a poll, which is a sample, and from that sample, we make an educated guess. So there's some of these states, like the hard blue ones, they're locked in. I mean, there's no doubt, no doubt that she's going to win California, and no doubt she's going to win New York. Pennsylvania was a lighter shade of blue, but now it's trending pretty hard toward 89% that it's going to go toward. Even Texas, there's some of these states that are traditionally Republican are now a little bit in play. I thought they were more in play than that, but maybe not. But anyways, it uses polls, and this is the timeline over the election. So June 8th to current. You can see around August it was pretty tight, but then some very bad things happened for Mr. Trump. And you can see these are predictions. They do 10,000 iterations of the election based on the variability at this point, and these are the projected margins. So if it's all blue on this side, that means like Washington, she's got that. These are like of the 10,000 outcomes. This is the expected, the dot. These are some of the outcomes were for Trump, and some very few there. So this is kind of a cool map and like an infographic. This shows the states by their worth, right? Not by the size, the geographic size, but the electoral votes. So it kind of gives you a better representation of where things are at, because our election is really a state. This is kind of cool as well. It starts with the ones who's most likely or almost guaranteed to win, least likely, and if you start over here, it's the same thing for Trump. They both have to get over that 270 line, so she would have to win Minnesota only, and even if she lost Nevada, Florida, North Carolina, Ohio, Iowa, and Arizona, she's still going to be president. They also talk about tipping point chance. Pennsylvania is the second most powerful state right now as far as tipping point. Florida's number one, and I think I saw in the paper, isn't Trump coming to Johnstown? Mm-hmm. Yeah, so that's why. So they run simulations, and from the simulations, the 10,000 simulations, So here's what I'm saying. Like, I get tired of going on Facebook and seeing all the crazy memes, because this election's over. I mean, it's just a matter of it. Unless something earth-shattering comes out, and I mean earth-shattering, it's over. The cake is baked. So, I would bet significant dollars on this election right now that it's going to go the way of the Democrats. So, and I know there's people that will hold on to any kind of glimmer, but stats do not lie. So we'll see. We'll see. We'll be in this class when the election happens, right? So right now, right, if you're making a decision saying, I know in the stock market, and I don't know this because some people are predicting that if Trump wins, the stock market's going to go way down, but other people are saying that's premature to say, and some people are saying if Hillary wins, the stock market is going to go down. But if you did have an investment and you said it's tied to the presidential election, we would be making that decision under risk, because we do have some probabilities associated with it, right? And these are pretty legitimate probabilities. If you look, there's also betting sites, like where you can bet on the presidential election, and they're about 85-15% as well. So it's pretty much over unless something comes out that is, and even at that, like a lot of states are early voting already. Like North Carolina, I think they have like a lot of votes in at this point already. So, anyways, so it's kind of a cool site. uses statistics, which you might enjoy. Instead of posting memes, maybe people can take a look at actual data. Okay, so let's look at another example of decision making, and we're going to talk first about decision making under uncertainty. And uncertainty means we have no clue what's going to happen about the future states of nature. Tom Brown has inherited $1,000. He has to decide how to invest the money for 1 year. A broker has suggested 5 potential investments: gold, junk bond, growth stock, CD, stock option hedge fund. The return on each investment depends on uncertain market behavior. Tom would build a payoff table to help make the investment decision, and someone built this payoff table for us. Okay, so they're saying if we invest in gold, for example, and there's a large rise in the stock market, we're predicting that the investment will go down 10% and we'll lose $100. If we invest in gold, there's a large rise, large fall. We're predicting it's going to stay even. So someone has put together this payoff table. Now what I want you to see is we have 5 decision alternatives. And the states of nature are definitely exhaustive, meaning everything's considered, right? Because we're using ranges. Like if it goes down 2,000 points, well, it falls in a large fall area. And it's mutually exclusive. It's either in this range or this range, which that's not exactly how things work, because difference between this category, 1 point in the Dow, and this category, pretty big shifts. But it's really not that big, right? So that kind of hurts us as well. But it's still a good tool. So if I gave you this table and said, what would you invest your money in it, what would you do? Okay, and I think we already have this. Yes. Okay, so what would you do? Well, before we do that, let's look at the bond and compare it to the stock option hedge. So the bond and the stock option hedge. What do you notice if we compare the payoffs for the bond to the payoffs for the stock option hedge fund? In each and every case, the bond is what? Greater than or equal to the stock option, right? So if that's the case, we say that the stock option alternative is dominated by the bond alternative, right? In each and every case, this decision is equal to or better, then we're going to throw that last one out, right? If in each every case this one's better, unless there's some other thing we were unable to model, we would throw that out because it's there's the slide. So we are going to learn 4 decision criteria under uncertainty to help Tom Brown make this decision. The max and min criteria, the min and max regret, the max and max, and the principle of insufficient reason. So let's go through them one at a time. Now these are kind of nice because the name kind of tells you what to do. The first one is the max and min decision criteria. This is used under uncertainty, which is the condition that we have. It fits both a pessimistic and a conservative decision maker style. So if you are pessimistic, you always believe that the worst thing will occur. And if you're conservative, you want to lock in a guarantee, right? So this kind of fits both of those types of decision makers. You can be both. You can be both pessimistic and conservative. Actually, usually those things do go together. So what we do under the max and min is we look across every decision alternative and we find the worst case scenario. So, and you guys kind of did that when we did our little example. If I invest in gold, the worst thing that can happen is I can lose $100. If I invest in bond, the worst thing that can happen is I can lose $150. If I can invest in stock, the worst I can lose is $600. If I invest in CD, the worst I can do is make $60. So I pick the maximum of all the minimums. That's what the max and min criteria. Pick the maximum of all the worst case scenarios. So if I use the max and min criteria for Tom Brown, what decision would I go with? I would go with the CD, right? Because it has the best worst case scenario. Okay, that's one approach. That's not so hard. The second approach that we're going to cover is something called the min-max regret. So the first one was max and min, pick the maximum of all the minimums. This is the min-max, so pick the smallest of all the maximum. It also has that word in there, regret. Okay, so what regret is, if you think about regret, regret is lost opportunity. This also fits both a pessimistic and conservative decision maker, but it has a slightly different focus. Instead of looking at like the actual payoffs, we look at lost opportunity or regret. The decision maker incurs regret by failing to choose the best decision. And let's go through this. And I want to show you how we build a regret table. So up above is our payoff table. Down below is our regret table. So we have to build a separate table to model regret. So if we look at a large rise, if a large rise occurs, what would have been the best decision for me to make? Stop. So if I made the best decision, if a large rise has, I made the best decision, how much regret do I feel? None, right? So that gets a 0. I feel no regret. I made the best decision possible, no regret, right? No regrets. I'm living my life with no regrets. Everything is now predicated off of that $500. Okay? If a large rise occurs, I could have made 500, but instead I invest in the gold and I lost 100. So I could have made 500, but I lost 100. That's $600 worth of regret, right? The difference between negative 100 and positive 500 is $600. I could have made 500, but instead I made 250. Hey, I made 250. I'm happy, but hell, I could have made 500, so I still feel $250 worth of regret. Does that make sense? Down here, yeah, I made 60. Okay, good. Always, making a profit, you don't go out of business, as Damon said. But hey, I could have made 500, so I feel 440 worth of regret. Does that make sense? So we go through every payoff. And let's do another one. Let's do small fall. So if I have small fall, what would have been the best decision to make? Full. So that gets $0, 0 regret. Everything is based on that. I could have made 300, but instead I lost 100, $400 worth of regret. I could have made 300, instead I lost 200, $500. Could have made 300, instead I made 60, $240 worth of regret. Does that make sense? You guys see how that goes? So I build a regret table, and then it's called min-max regret. I pick the minimum of all the maximums. So if I look at the regret table, if I choose gold, the biggest regret I can have is $600. If I choose the bond, the biggest regret I can have is $400. If I choose stock, the biggest regret I can have is $660. If I choose CD, the biggest regret I can have is $440. Just going through our things. So I want to pick the minimum of all the maximum regrets. It looks like in this case, I would choose bond. Okay, so 2 different decision criteria, same payoff table, 2 different decisions. Okay, both conservative, both pessimistic, 2 results. Yes? The third one that we use under uncertainty is kind of what Laura used when she said I'd go with, I can't remember what it was, but the big one, right? The easiest one. The third one fits an aggressive or optimistic investor, the go big or go home kind of person, right? So it's called the max criteria. And the max criteria is based on the best possible scenario. We think the best thing is going to happen, so we go with the maximum payoff. So the maximum of all the maximums. All you really have to do for this one is look into the table, find the biggest number. I think the biggest number here is stock, it's 500. So we would choose stock, okay, which is the third investment. So 3 different decision criteria, 3 different decisions. The fourth one is probably the worstly named one. I don't know if worstly, that's probably not a word either. It probably has the worst name. It's the principle of insufficient reason. Okay, I don't know if you'd want to put that in a report to your boss. Why did you choose this? Because the principle of insufficient reason doesn't sound good. But what it's saying here is, hey, we don't know what the heck is going to happen. We really don't have any reason to make this decision over this decision. So since everything is equally likely to happen, we have no clue, all we're going to do is pick the one with the highest average payoff. So if we looked at this, and I don't know if this criteria, if this table is right, but we could go through here and we could add up all the payoffs for gold. So this would be 500, I believe, for gold. For bond, it looks like it's, 450, 600, 500, 350. For stock, it's 850, 650, 50. This would be 300. So we add them all up. The highest average payoff or the highest total payoff looks like it is gold. I think these numbers on this slide are wrong, but I think it is gold. I think this is $500, so it is gold. So it's not so. So anyways, we went through 4 different criteria and have 4 different decisions. So what good is this? Well, it's looking at it through an unbiased lens, right? So if we did this, say we did these 4 criteria, we applied that to a payoff table, and 3 out of the 4 said go with decision 3, buy, I don't know, the stock. That kind of says, you know what, if I'm insufficient reasoning, if I'm a little bit pessimistic, if I'm a regret, go with this one. The only way I would go outside of this decision is if I was being very aggressive. And I still might do it, right? I still might do it. But it helps you frame a decision with no emotions, right? No emotion saying this is what we modeled, this is what the result was, go with that decision, or maybe don't go with that decision, but it kind of gives you some information where you did not have information in the first place. You're going to see, and I'll show you that in a second here. There is a very nice Excel spreadsheet, not a very difficult one, that does this for us. So if we look under Chapter 6, under Decision Payoff Table Template, bring this up. In column A, we put our decisions. In column B, we put our states of nature, where they intersect. I'm just going to make up a table here. We put our 200, 150, 150. Put our payoffs, and down below it says if you're using the max-min, go with decision 2. If you're using the min-max regret, go with decision 3. If you use the max-max, go with decision 3. If you're using principal insufficient reason, go with decision 3. So in this case, I have 3 of the 4 pointing to decision 3. So unless I am very, very what? Very, very risk averse, very conservative, very pessimistic, my decision 3 is the best way to go. Okay? My decision 3 is the best way to go. All right, so here's what I'd like you guys to do. It's only 7:15. I'm going to build a little. I have one on here. I'm going to build a little payoff table, and I want you guys to take a few minutes and apply these 4 criteria to it. So there's a payoff table. I'd like you to apply the maximum in, the minimax regret, and the principle of insufficient reason. And maximum. Okay, so let's apply all four of these. So the first one is the maximum, meaning we pick the maximum of all the worst case scenarios. So we go across the decisions, we say, hey, worst case scenario here is we make $100. Worst case scenario is we lose 500. Worst case scenario is we lose 100. We pick the maximum of all the minimums. Under the maximum, I go with decision one. You guys get that? Yes? Okay. Minimax regret, I have to build a regret table kind of that mirrors this down below. So the way we do that is we start at every state of nature and say, hey, what's the best thing that could happen? Well, state of nature 1 occurs. Best thing would have been to pick decision 2, so that's 0 regret. I could have made 500, instead I made 100. That's $400 worth of regret. Could have made 500, instead I made 250. These regret values will always be positive. They'll be 0 or higher. We'll never have a negative regret. The state of nature 2 happens. Hey, 200 bucks is the highest one. Oh, that's $700 worth of regret. That's $100 worth of regret. State of nature 3, that's $100 worth of regret. And that's $300 worth of regret. So hopefully I get my regret values right. So in this case, this is mini-max regret. So I look at the worst case scenarios. Hey, $400 is the most regret I could feel if I make decision 1. $700 is the most regret I could feel if I make decision 2. And $300 is the most regret I can make if I take decision 3. So under the minimax regret, I would choose B3. Yes? Max is the easiest one. Find the biggest value. Well, the biggest value in this table is 500. So max, go big or go home. I pick decision 2. Finally, principle of insufficient reasoning. Add them all up, pick the highest one. That's 300. That's 200. That's 350. That would be decision 3. Okay. So 4 principles, 3 different decisions. Let's use Excel to do this. I think I have. So decision 1, decision 2, decision 3. I add into my payoff table. You'll see down below, max and min, it says, hey, use decision 1 that has a minimum payoff of $100. Then max regret, use decision 3 that has a has the most regret you can feel is $300. Max of max, use decision 2. The best possible payoff is $500. And insufficient reasoning, the highest average payoff, because there's 3 states of nature. I think that averaged to that totaled to 350. 350 divided by 3. That's where that 116.667 comes from. Make sense? All right. So let's take this same scenario and let's apply the concept of risk. Okay, so risk means there is probability involved. Right now, I know nothing. Okay, I know nothing. If I told you there was a 90% chance that state of nature 1 was going to occur, what do you think you'd do? What do you think you'd go with? If I told you there's a 90% chance of state of nature 1 occurring, what would you do? Nick? And say, hey, that's more likely, it has a big payoff there, I'm going to go with that, right? So I want something, I want a method that factors in both the magnitude of the payoff and the likelihood of the payoff. I want something that factors those 2 things both in. What does that? How could I do that? How could I factor in both the likelihood and the magnitude? Let me give you an example. I have a 16-year-old son. It's tough. Okay. Me and my wife paid for 2 cars. We paid annual car insurance of $900. Well, before my 16-year-old son started driving, we got a 3rd car, and now we insure 3 cars, and we paid $2,600 for a year. Okay. Why? So, what does the insurance company's payoff table look like? What do they care about? They don't care about me. They might say they do. They don't care about me. They don't care about my son. What do they care about? They care about payouts. They don't care about accidents, really. I mean, they care, bottom line is they care about payouts, right? So they have a table, and they have payouts on that table, like expected payouts for 46-year-old male driving a minivan, you know, well, I had a couple of but overall, pretty good. My wife's perfect. So they have a table, and they're like, you know, $900. You know, that's pretty good. So they have expected loss of maybe $500 on me and my wife before, annual loss. That's expected payout. So why do they charge me $900? Why? Their expected loss on me or payout is $500. They charge me $900. Why? Because they want to make a profit. That's why it's called a premium, because it's a premium above what they expect to pay out for you, right? But when my son started driving, they looked at him, they said, 16 years old, and they don't know, I think he's probably better, he's a pretty good driver, I think, you know, knock on wood. I think he's a pretty good driver. But he's paying for what? He's paying for the sins of all 16-year-old boys, right? There's a lot of sins there, right? There's a lot of sins to pay for. So they put him in there and they said, hey, the likelihood that a new driver, no prior experience, and a boy to boot, right? We're worse, is they put the probability up, and that meant the expected loss on my 3 vehicles went from $500 to perhaps, I don't know, maybe $1,400, and they still double it, so it's $2,600 is what they charge me, right? And I didn't say like, hey, you're discriminating against me. I'm like, I get it, right? I understand what you're doing there. So what is the criteria that they use to do that? What is the criteria that they use to do that?
How many others has seen those gotten after?
So they figure out the probability, they have actuarial tables for sure, they have a lot of things they can study, areas, if you're in a different metropolitan area, you're going to pay more, all that stuff, right? They have all that. But what does it come down to? What's the criteria? Yeah, I know you guys know it. Yes? Yeah, you've heard of the expected value criteria, right? Expected value does this. It's a very simple formula, but it's a very, very powerful formula. The expected value of X, sometimes called like the weighted average of X, looks like this. We take every value times its probability. Remember I said we need something that takes into account the magnitude of the payoff and the likelihood of the payoff. This doesn't. This is summation notation here. It says take every payoff times its probability and figure out a weighted average, right? That's what it does. So when, say the insurance company had a table, right? They say, for the MECOs, as it sits, there's a 90% chance that we don't pay them anything this year. Maybe, let's say, I think I have $1,000 deductible, so maybe 5% of 5,000, maybe 4%, 20,000, and then there's the catastrophic ones, like 300,000 they pay out, and that might have been 1%. Well, when Lucas started driving, right? So they factor that in, and maybe expected loss. I didn't do the math, but expected loss was 500. But when Lucas started driving, maybe this went down to 85%, and this went up to 9%, and this, so the expected loss on us changed, and they adjusted accordingly. Does that make sense? So in this case, I would want to do the same thing, and they did it in his head. He said, if I said there's a 90% chance of state of nature 1 happening, and a 10%, or we at least have to add to 100% obviously, and a 5% chance of this, and a 5% chance of this, we're going to take everything up here. We're going to say 90% times 100, 5% times 100, 5% times 100. We add it up. The average, the expected payoff for decision 1 is $100. That makes sense. If we look at this one, it'd be 90% times 500, 5% times negative 500. That comes up to 435. If we did decision 3, I'm not going to do the math because the highest one, the highest expected payoff is decision 2, 435. If I change these odds around, and I change this to 5% and this to 90%, well, guess what? That decision criteria adjusts accordingly, right? And it says, hey, if that's 90% likely, that negative $500 is going to get 90% of the weight, and that positive $500 is only going to get 5% of the weight. So it does exactly what we're talking about. It takes the magnitude times the probability, sums it up, and figures out a weighted average. Okay? It is a simple, elegant thing, but it's a beautiful thing. It's the thing the whole insurance industry, home insurance, car insurance, life insurance. About 5 or 6 years ago, I got a term life policy. I think it's like $1 million policy, which is kind of cool, right? More than $1 million. So, dead. So anyways, before they gave me that policy, and I think I only paid $450 a year, $475 a year, something like that. Before they gave that policy, what did they do? Before they issued that policy to me, what did they do? Yeah, they came to my house, they took my blood, they put me on a scale, they asked me about my parents' health, they checked my arms for needle marks, right? All that stuff. What kind of risky behavior do I mean, they asked me everything, right? And what they were trying to figure out, they took cholesterol, all that stuff. they were trying to figure out, and they don't say it, but they're trying to figure out the odds that I'm going to die in the next 20 years, right? And if it's too high, they don't give you an insurance policy, right? So because they're factoring in, not just you, they're factoring in all the people that they paid all the premiums and never died. So if you die, they pay it out because they have, they have the numbers worked out. Same thing with gambling, right? You go to Las Vegas, you go to Atlantic City, you go to Rivers Casino. It's all based on expected value. They know the odds are in their favor, so for every winner, there's going to be 2 losers, right? They want more and more people playing. So that is, and that's the only one we're going to cover when we do decisions under risk. Expected value is the dominant method, okay? Even if you think about it, if you have a bad credit score, you're going to pay higher interest on a loan. Why? Why are you going to pay higher interest? You're like, I have a bad credit score. Why are you taking it out on me? If you look at it from the bank side, bad credit score means less likely to pay back. So for every one of you that doesn't pay back, we need to make more off the people that do pay back in your demographic, right? That's why. That's how that works. It's called expected value. Now, expected value is very good in decision making for decisions that happen over and over and over again. For example, I've had home insurance for 25 years, have never had a claim, right? So the expected value on my end is bad, right? It's bad. But why do I get home insurance? I don't have a mortgage, so I don't even have to have home insurance, but I do. But maybe in Pennsylvania you do, I don't know. But why do I? Why do I?
Cost of replacement is
Catastrophic, right? I can pay whatever they charge me, which goes up every year, but cost of replacement is catastrophic, right? So on the insurance company's side, they're using expected value because they can insure my home against all the other homes, right? If my house burns to the ground, well, great. These other John Mikos, their house didn't burn to the ground. On my side, I'm using something called expected utility. So let's take a little break. I've gone an hour here. We don't have a whole lot to do after break, but let's take 10, come back, and we'll do a couple other things in chapter 6.
Like I typed in the probabilities and mine
Didn't change at the bottom?
Is it yours?
I don't find
No.
Well, I think your expected value came in, right? No, it didn't.
Do you say hashtag name question mark?
Yeah.
I'm sorry, what's wrong?
Our, maybe the formula for the expected value didn't change.
Which part?
Mine and Alex's, neither one of ours changed. I could put it in the probability, but there's,
It has to add the 1, so you have 9.
Oh, yeah, you have to put .05. You have to put .05. Yeah, it's 5%. Yeah, there you go. There you go.
It has to add them. I think you didn't have that. You didn't have that.
Sometimes, like, I have issues with Excel, and I just close it down and set new. Okay. So if I reopen it, should.
Yeah, but I'm not sure why. When fixing, it's giving you the right number, it says 435. It's a line and blow it up. Right.
I can't even imagine
So the GAN chart. So what are you gonna do with the front part? All right. Go ahead, yeah. Yeah. Yeah, so you current value management, you know,
I reopened mine and put the numbers back in, and it worked.
Yeah, as soon as I added, I didn't have enough.
Oh, yours
As soon as I
just changed
put
it
the
then.
0.05 in, it came in.
Okay.
Ryan knew. Yeah. Ryan knew because. I know.
We could do it as, yeah, because each department has daylight. So then no, it's like we give the staff information and we measure them out. Who's gonna cover who? But so that would the person that does this has like maybe the first, second, and third shift. And first shift is
Yeah, I mean, it's up to you if you want to do it at all, but I don't. Okay, right. I mean, if you want to. I would just say,
yeah, because I'm doing just garments.
They're not like full-time, part-time.
So we could do
That was somewhere you might want to know.
Right. Would you want to try to give yeah, or
But then you're also having other departments. Every department has to take turns.
somewhere in there until they can get it.
Do the other departments make it?
You know what I mean? Like maybe that's what you did with that.
You guys make
Yeah, to play with a couple different, I don't know if that's the case.
It is, yeah,
That is the case, so maybe being fair, rotating short is one suggestion, it might be different to play. Your department has to fill in the overtime. But then
because they all have to.
so there's different, there is interesting.
Okay, so, I'm still recording. In this section, in chapter 6, I would say the only thing that's a little conceptually difficult to understand is this concept of expected value of perfect information. Okay, so I think we're clear with what expected value is. So every decision has an expected outcome, right? We take all the payoffs times its probability, and we say, hey, that is the expected payoff, for that decision, expected value of that decision. Switching those probability values will change that payoff. It'll give more weight to whatever that state of nature is. Well, there's something known as EVPI, expected value of perfect information. And what it is the gain in expected return obtained from knowing with certainty the future state of nature. So think about this. Okay, I know what my expected value is, and let's just go to the one we did earlier. So I don't know, I'm going to make these odds a little better. I'm going to say 40, 30, and let's say 30. Okay, so I'm going to spread them out a little bit. And they do have to add to 1 or you will get an error. And right now it's telling me the expected value is decision 3 is $130. And then we see something down here, expected value of perfect information. Okay, what that means is if we knew exactly what was going to happen, the difference between what we expect right now, which is if we make decision 3, we're expecting $130, and if we knew what was going to happen, we could have a premium of $190 and follow me here. So if I knew decision 1 was going to happen, what would I choose? Obviously, I would choose what? That's $500, okay? If I knew state of nature 2 was going to happen, what would I choose? Which one? Right, that's $200. And if I knew state of nature 3 was going to happen, 2, and I get $200. Okay. If I knew that was going to happen, that's exactly what I would do. But before I go and do that investigation, I don't know what I'm going to find, but I know there's a 40% chance of this, a 30% chance of this, and a 30% chance of this. So let's see, 500 times 40 is 200. That's 30% out of 200, that's 60. 30% of 200 is 60. So it looks like I have 320 here, okay, 320. So the expected value right now, okay, is 130. If I knew what was going to happen, it would go up to 320. If I knew, if I could pay to someone to figure out what was going to happen and then make the right decision, I'm expecting that to be worth 320 because I don't know which of these is going to happen. 320 minus that original 130 is what? Because 130 is what we're expecting right now, is that 190. Does this make sense? No? Yes? So the way you use this information, if I see this number, and someone says, well, I could do more analysis. I could go out and do more surveys. Maybe I could pay for that information. How much would that information be worth to me? How much do I expect that information to be worth to me? And if it's a big number, well, then maybe I go out and do that extra analysis. If it's not a big number, then I say, well, let's just go with that decision. So I'm going to change this back to where we had it. Okay. And now I'm saying, hey, the expected value of perfect information is only $35. So why not go out and do that effort to try to figure out what's going to happen, right? To try to clarify what's going to happen and pick the best decision. So if that's a big number, hey, and you can do more information, more research, take more polls, more surveys, then hey, maybe it's worth doing. You know, but if it's a small number, probably not. Do you guys get that? What that concept mean? Yes? Okay. All right. The last thing we'll cover in chapter 6 is we're going to talk, I mentioned it earlier, we're going to talk about the difference between expected value and utility. So utility is the usefulness I get out of a decision, right? The happiness, you know. If you think about utilitarian society, it means everyone's happy, right? Utilitarian. So when we talk about utility, we're thinking not about the payoff in hard dollars. We're thinking about the usefulness of it, the utility, the value of it to maybe a subjective person. If we always made decisions based on expected value, none of us would gamble. Okay? None of us would buy insurance unless we knew the odds were in our favor, and they aren't. None of us would play the lottery, all those things. Yet we do, right? Because there's a difference between expected value and expected utility. When I said, why do I insure my home? Because paying that premium every year, yeah, I lose a little bit of utility, right? That $600, I lose a little bit of utility, $600. But if my house burns down, that's catastrophic. And if I don't have insurance, that utility is crazy big, right? It's outweighs the size of the financial loss, right? Because it ruins me and my family. So what we try to do, and this is is utility is a very subjective thing. If you think about it, $1,000 to me means a lot. $1,000 to Warren Buffett means little, right? So $5 to my 8-year-old son is a great thing, right? $5 to me means very little. So utility, when we talk about payoffs, is a little bit different. So we have ways or approaches that we try to assign utility for various people. Now, has anyone ever worked with a financial planner? Like started at the beginning with a financial planner? Recently, no. Okay. One of the things they will do is they'll talk about, what are your goals, right? They'll say, what do you want to? I want to retire here. I want to put my son through college. I want to blah blah blah. But another thing they do is they try to assess like your personality. They try to assess like how risk averse you are. Like, they have like personality things, because what they're trying to do is figure out your tolerance for risk, but also how much utility you get out of various outcomes. This is an approach, and it's kind of a kludgy thing, kind of a goofy thing, but it's a way to, by person, assign utility to payoff value. Right? So here's what we do. We take a payoff table, and we list every possible payoff in the payoff table in ascending order. So from the worst to the first. The worst payoff gets a 0, meaning 0, that's the worst thing that can happen, so it gets a 0. 0 happiness. The highest payoff gets a 1 because it's the best thing that can happen, right? So 0 to 1 is my scale. Every other payoff in that range is shades of gray. Okay, so let's take, okay, this was the Tom Brown, I think. This was the Tom Brown one. And the highest payoff was $500. The lowest payoff was negative $600. The highest payoff gets a 1, the lowest one gets a 0. We asked the decision maker one question, okay? What value of P would make you indifferent between the two situations? So we can get the current payoff, and that's what we try to assess, or you can play a game where you got the highest or the lowest payoff. What value makes you indifferent? It's called the indifference approach. So let's do this with someone. And your value is going to be different than this person's value. So I give you, let's pick on Haley. Haley, you have $300, right? Or you could play a game where you make $500 or lose $600. How certain would you have to be before you'd be willing to play that game? You have $300 in hand. How certain would you have to be of making $500 as opposed to losing $600 before you'd be willing to play that game?
You're asking.
I'm asking you personally. It's not, there's no wrong answer. Okay, so this person said 90%. You're different than that person. You're saying, well, I'm a college student, I'm not wealthy, so I'm not gambling at this point. So you're saying 95%. We would go through every value the same thing. Let's take, I don't know, 0. Okay, so right now you have nothing. You can play a game where you make 500 or lose 600. How certain would you have to be of making 500 versus losing 600 before you'd be willing to play that game? So you have nothing right now. How certain would you have to be of making 500 as opposed to losing 600 before you will? How certain would you have to be of making $500 if you willing to play that game?
I'm just confused right now, sorry.
If me and you are going to play a game, there's two outcomes. You make $500, you lose 600. Okay? You have nothing right now. That's what you lose, right? You have nothing right now. How certain would you have to be of making 500 before you'd be willing to lose 600? How certain of that outcome would you have to be? It doesn't, it's up to you. What do you think? I probably would say, I don't know, I'm kind of a gambler. So I'd probably say, I don't know, maybe 50%. But maybe you'd say, well, I can't afford that negative 600. That's catastrophic to me. So you'd say, I have to be more short, Dr. Meek. I have to be 90% short, right? My numbers and your numbers would look different, right? Does that make sense? Do you guys know what I'm saying here? So we would go through those outcomes with the person, and we would replace the payoff values with the values, we replace them with utility values. So it's a way of assigning personal utility to values in the table. So go ahead.
So these don't have to be evenly spaced out by any means. It doesn't have to be
No.
Okay.
Because humans aren't logical, right? So we're asking, like, subjectively how certain you would have to be. Now, what they should do, though, is they shouldn't be spaced out. They don't need to be spaced out. But if you think about the nature of the game, it should be descending, right? Because you're saying, well, I have $300 in it as opposed to $250. You know, okay, I can deal with less certainty there, right? Because I don't have $300 in hand. So they should be descending all along. And then what we do, and I'm not sure if this example goes through and does that, but we take that payoff table that had numbers in it. Remember, it had the 600, the 500, those kind of things. And we replace those payoffs with those utility values that we just figured out for that individual person. And then we say, instead of doing expected value, expected payoff, we look at expected utility. utility. Now, I don't do that in class because it is kind of a goofy thing, but I do want you to understand the difference between expected payoff and expected utility. Utility is different for each one of us, right? It is different. All right. Any questions on that? So chapter 6, I think, is probably one of the most reachable chapters in here. And what I would like you to do for homework is, let's see, on page 375. Do number 2. Do number 13. Uh, 20. I'll tell you what, do 22 as well. I don't have it up there, but I'd like you to do 22. Which leads into 23. So 22 and 23 are like combo. So 22 and 23. That's it. You don't have to do those others. Okay? So week 9 is over. Week 10 is next week. We're getting closer to the end of the course. So if you have any questions about your group project, I'd be more than willing to answer them. Have a good evening. I'll see you next week.